Basically, today's practice exercise is not long. We did it yesterday, and the idea is to practice the equivalence of deterministic and non-deterministic finite automaton. So basically, the lecture 4, the second part of Unit 3, was related to equivalence of deterministic finite state automaton and non-deterministic finite state automaton. Please pay attention that homework 3 was delayed till Sunday. Homework 4 will be at regular time, but what I did, I gave you less homework. 4 is actually a relatively easy homework. The topic is the topic of current lecture, but the homework itself has a small number of questions in it. So basically, I know that you have a more day bed, the second the exams. So I decided not to cancel the homework, but please pay attention that next week you have to submit basically 2 homeworks, homework 3 and homework 4. Okay.
Rina,
So we will.
before we start, may I ask a
Okay.
question?
Yes, definitely.
Yeah, so I know we're practicing now, but can we go over the lecture itself that was online? Like
Yeah. Let's
groups?
finish. Let's finish practicing, and if someone has questions, so we will. I will answer the questions.
Okay, thank
So
you.
let's start with the practice, the part that everyone is interested in, and then if you have any questions, the same actually we did yesterday in the Hebrew group. They had some question related to the proof, so I did the proof once again. Not a problem, but I think it was only for 5 or 7 students who were interested in this question. Okay. So we start from the examples that I gave during the lecture. You are given concatenation of 2 languages. The first language is 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, and it continues. Concatenation with 0, 3 zeros, 5 zeros, and so on. The first question I would like you to ask, I will give you something like a minute or 2 minutes to do it by yourself. Give a formal definition for language L1, then for language L2, and then for language L1 concatenation L2. Okay? I asked the Hebrew group if they want to work in groups. They told that not. So I think you will probably think the same. So I'm giving to each of you something like 2 minutes to give the formal definition for L1, L2, and L1 concatenation L2.
Rina,
Mm-hmm.
the definitions that you just asked us was in the presentation.
The final definition, but we will talk about it. Was it correctly defined, not correctly defined? Okay, I will do some polling during this during the presentation or practice to know what happens with you, to know if to wait for you. Okay, okay, majority didn't finish, so it's okay. I will give you additional half minute or minute. Okay. So let's start with the first language. Yesterday, some of the students told, how do we know which language it is? So basically, I would like you to check two things. The length of the words. Maybe you have some sequence that is related to the length of the words and the structure of the words. So let's say that the first language is not well defined and you don't see currently what happens in this language. So I'm starting to look and I see that I have a word of the length 1 and of the length 2 and of the length 3 and so on. So definitely not the length is a problem or is a trick here. But I see that the first word is 1. The second one is 0, 1, and then I have 1, 1. Then I have 0, 0, 1. So I start to see that I have the same structure of the words. I have the words that have 1 at the end of the word. So basically that will be the definition that I will give. The definition will be that the first language is the language of all words that ends with 1 over our alphabet. The second language I understand was relatively easy. Nobody made a mistake. So the question was, how do we write the formal definition? And you have several possibilities. The first possibility to do what I did with the first language, to give the definition which is only words, W such as W has an odd length. The second definition can be written in a little bit different way. That's what I did. W equals 0 in power of n, where n is an odd number. So basically we have 1 0, 3 0, 5 zeros, and so on. And the concatenation of L1 and L2, the definition was given at the lecture, this one. This is a copy paste from lecture slides. So during the lecture slides, the following definition was given, that we are talking about binary strings, since we are having alphabet 0, 1, that end with a 1 followed by an odd number of zeros. So basically this definition is okay. Additional definition can be given using the definition of concatenation. So I can define that L1 concatenation L2 has the word W such that W can be divided to some prefix U and some suffix V, and the prefix U is a binary string that ends with 1, and the suffix V is a string with an odd number of zeros. Any questions until now?
So why don't you just say that U is in L1 and V is in L2
Oh,
instead of writing it?
exactly. If L1 and L2 are presented at the same question, you can also write U belongs to L1 and V belongs to L2. But if the definitions, the formal definition of L1 and L2 are not presented at the same question where you prove or give your definition, then you can't use it. But in
Okay,
this question,
but here it's presented.
yes, exactly. In this question, since L1 and L2 are described before, you can use the belong sign and to tell that U belongs to L1 and V belongs to L2. Definitely.
Okay, and just one more question, please. What else would you check besides the length of the word? I'm talking about L1 now. So besides the length that we checked and that we saw it's insignificant, and then you check the end of the word. So you saw one. Besides these two, what can I check?
Structure of the word. You can have or some prefix, or some suffix, or some substring.
Okay.
Here, I actually liked this question because this question is relatively difficult to understand what was the language. So I liked it, and this question was a right question to give during the practical exercise, because definitely yesterday we had a discussion about it, because some student claimed, listen, we didn't see this definition at all. So how do we do it during, for example, during the exam? So hopefully during the exam, the definition will be relatively easy, but once again, it will be different stuff during the exam. And sometimes you can't see the solution during the exam. So it's a problem. That's why we practice, we have lectures. By the way, I will give additional exercises solved by me. I will upload to the course page for this as a practical exercise. Okay, the next.
May I also ask a question?
Okay, yes, definitely.
L1, isn't it a bit too broad, all the words that end with one? For example, the word 101 would not be in there?
No, it will be here. Look, they started with suffix one, and then they're looking at all prefixes 0, 0, 0, 1, 1, 0, and 1, 1 will be there. You just finish. The next word here, I think, will be 101, and then you will have 110, sorry, 111, and then you will move to the words of the length 4.
Okay. I don't see it straight away when I look at the
Exactly,
readouts.
exactly. That's why I actually liked this question, because it was difficult to see the language itself. Okay, the next question. Please build the automaton. You can use non-deterministic finite automaton for L1, and please build an automaton for L2. I think 2-3 minutes will be enough, because it's not a difficult construction.
You want to build a DFA or NFA? I didn't get it.
It doesn't matter. Now, when we learn NFA, if NFA is easier, you can use NFA. Okay, let's see how are you doing. I'm asking the same question. Did you finish this question? Okay. Okay, I see that majority of students finished, so we will continue with the solution. Okay, how many states do you have in automaton for L1?
2.
2 states. Okay, so we have something like this. Q0 we have one transition to Q1, and we have some prefix 01. We have a self loop in Q0. So it's definitely a non-deterministic finite state automaton, and it's good enough to give the formal to give the automaton for this language. So L2, how many states do you have?
2 as well.
Also 2 states. So we have moved from state P0 to P1, an accepting state. And then for every 2 zeros, we return back. For students who are using the solutions from previous semester, please pay attention that a mistake was at the solution of the lectures, they draw the self loop with 1 was drawn here and was drawn there, and it's not okay. Because if I have a loop with ones, then I can accept not only zeros, but also other words. So basically, I don't write anything about ones, since the definition of the language was only zero related.
So this automaton without one for L2 is also non-deterministic.
Exactly. The automaton here
Okay.
is also non-deterministic finite automaton. Okay, the next question. I would like you to build an automaton for L1 concatenation L2. And basically, it's the same idea that we did during the lecture, but now you will do it yourself. I just would like to check what happens. Okay, you're 50-50, so I will give additional time, additional minute, and then we will continue.
So Rina, what happens if you input, for example, 0 from Q0 to Q1 in L1? Because in the non-deterministic automaton.
So for 0, you stay in Q0 in L1.
So for M2, if I input 1.
You go to an empty state, to the trap state.
Which we don't see.
Which you don't see, but it exists. For example, if you were asked to build a DFA, so for DFA, you are missing one state, this state, and you will move here with one from here and with one from here.
Okay, so every automaton has this invisible state.
Yes. If
Okay.
you have missing transitions, it goes to the trap state. That actually what we did during the last practical exercises. We were asked to build DFA, and then we were asked to build NFA. And what I did from the transition from DFA to NFA was that I just deleted the trap state.
Okay.
Okay, I would like to remind you the idea. So the starting state of L1 concatenation L2 will be the starting state of the first automaton. From the accepting states, we will move with epsilon transition to the initial state of the second automaton. And we will delete the accepting state here. And the accepting state of the resulting automaton will be only P1. So let's see the final drawing. And let's give a formal definition. So some student asked, how can they give now the formal definition of this automaton? So please pay attention. I did the renaming of the states. Previously, I have in previous slides, I had states named Q0, Q1 and P0, P1. Here I'm using a little bit different notation. I move to R, but if you don't like it, this state can be Q0, this can be Q1, this is P0, this is P1 from the previous drawing. So I would like to define the 5 tuple of this automaton. So let's start with Q. Do we have any additional states, or we have all the states of the automaton M1 and all the states of the automaton M2?
We have all the
Yes.
states.
Okay, so we are writing union between Q of M1 and Q of M2. Alphabet, sigma is the same alphabet, so basically I can write equals to sigma of M1. It will be enough. Transition function, let's start talking about delta function. I didn't delete any transition functions that we had in the first automaton and in the second automaton. So I will start from delta M1 union with delta M2 because I'm keeping all the transitions that we had, and also I'm adding union, a new transition from the state delta, from the state R1, which was an accepting state, with epsilon transition. I'm moving to the state R2 in this automaton. This is an additional transitions that I did here. If I want to give a more abstract definition, so I will write here that I do it for every state R in FM1. Once again, if you give an abstract solution, not a specific solution, so you have to specify that you will do this epsilon transition, you will add this epsilon transitions for each state that was an accepting state at automaton M1. So for each state that belongs to FM1, you will define this transition. But in our solution, I don't have to write it because here we have a concrete solution, not an abstract solution. We have a concrete automaton. Okay.
Can you repeat the comment, Rina? I didn't understand the comment.
A comment? Which comment? What I did before?
No, what you said about the F right now.
Okay. Yes. Sometimes you have to give a solution for the specific automaton, like here. So for the specific automaton, I see that I've added only one epsilon transition. So it is easier for me just to write a delta R1 epsilon equals R2. That's it. But if I have some abstract solution, some machine M1 that I don't see M1, but I know that it exists, I have to write their definition, the more correct definition, and I have to mention that for each state, let's call it R, small r, that belongs to the F of M1, final states of M1, I will define this transition.
Great,
So
thank you.
this will be written here before the transition function. Okay.
Rina, can I ask a question, please?
Yes, but let's finish and then I will answer all the questions.
Okay.
Okay. In initial state is R0. So Q start, QS equals R0. And the set F has only one state, R3, which is a final state of the second machine. So if someone writes that F equals to F of M2, it is also a correct definition. Okay, now all the questions.
So can I write R2 as the accepting state? And then instead of epsilon, just write 0. And
Where
cancel R3. Yeah, let's say R2 is an accepting state now. This is 0. And R3 is a rejecting state.
Yes, you can do it.
So, okay, so now this is my question. In everything we learn, we're trying to be efficient and stuff like that. But I don't understand the automaton idea. Like, what is this? What am I doing?
No, here the idea was that you look for the easiest construction, because you already used your brain. You saw the construction, what you have at the second automaton, and you improved it. The idea with the construction of concatenation is a very easy one. Just wait, I will take a notation. Take M1 as is. Take M2 as is. And for every final states in M1, build an epsilon transition. And don't look for improvement. What you already did, you are started to build an equivalent DFA. For example, if after my construction I will be asked to build an equivalent DFA, I will definitely have the transition from R1 to R2 with 0.
But what I said is not DFA, because what I said
it's
doesn't...
not DFA. No, it's not DFA. It's still partial DFA, but you already started the equivalence.
Okay, but partial DFA is an NFA?
Yes, definitely.
Okay, so
if you have for one input letter in one state the missing transition, you have an NFA.
Okay, so what's simpler? You said I'm looking for the best automaton. So what is simpler? The one with epsilon or the one I said with 0?
The one with epsilon is easier to construct. You don't have to use your brain to understand that this 0 transition can be used here. With epsilon, you just draw epsilon and you don't improve, don't change accepting and non-accepting states. But your solution is also correct solution.
Okay.
Your solution was already one step towards DFA.
Okay, thanks.
Okay. The next question. You are given non-deterministic finite automaton and you are asked to build an equivalent deterministic finite state automaton. I would like to remind you the epsilon transition function, that you can move from one state to another state without reading input. You are using epsilon transitions only. So basically the idea here is to start drawing. You start your solution with epsilon closure of Q0. And then for each input letter, you check to which states you can go. You unite all the states, and you also use epsilon score for those states. So let's start to solve this question in stages. The first stage, I would like you to ask to define epsilon closure of Q0.
What is epsilon closure?
Where you can move from Q0 using epsilon only.
You want to ask him to answer or to write it yourself?
You can write it in chat to give other students time to answer. Okay, so let's see. we have to start to build an equivalent DFA from epsilon closure of Q0. Epsilon closure of Q0 is, first of all, Q0 itself, if I don't use any epsilon transition, but I also can move with epsilon transition to Q1. So I will have the state Q0, Q1, and will the state Q0, Q1 will be an accepting state?
Yes,
Yes, why?
because of Q0.
Okay, if I have a union of several states, even if I have one state which is an accepting state, the whole new state is an accepting state. So Q0, Q1 is an accepting state. And now the next mission for you, or the next task, you have to write where can you go with an input letter A from the state Q0, Q1, and on the input letter B on Q0, Q1.
So you're trying to get rid of the epsilon?
I try to build the get rid of the epsilon and to build the deterministic finite state automaton.
Okay, so I can't have the epsilon in deterministic in DFA.
No, no, no.
Okay.
In DFA, you have only states and only one transition from each state with each input letter. Epsilon is not an input letter, it's an empty word. So once again, we are currently solving the question, giving the new start state, initial state Q0, Q1, where do we move with A and where do we move with B?
Isn't it maybe if we write the definition of the language, it will be easier?
Definitely not.
Like if we know that it must end with A and be, I don't know, even length.
I don't think that it's the definition of this language.
No, it was just an example. If I know
here, I think the definition is very difficult. It's not something very good defined, the automaton. So basically, don't start as algorithm that I used during the lecture was how do you construct an equivalent DFA? And the idea is very simple. First state, you start with epsilon closure of Q0. That's what we did. Now you have one state. You look for transition with each input letter. I will do it in a moment, the transitions, and we will talk how did we did it and so on. Okay, let's see. Let's start Q0, Q1. Okay, so I'm moving to this slide where I have everything written down, and the automaton, if you look, it's in the corner of the slide. So Q0A is not defined. It's a phi, an empty state. Q0B also not defined. And Q1A, I can move to the state Q2 or Q3. So I have the union of Q2 and Q3. And now I also have to do an epsilon score on this resulting state. So epsilon score on Q2 doesn't give me anything. Q2, we don't have epsilon transitions. Epsilon score of Q3 moves me to Q2. So I'm actually staying at the same state, Q2, Q3. And Q1 on B, Q1 on input letter B, we move to Q2. And epsilon score of Q2 is Q2 itself. So the result is, let's see the result. Okay. The result is that on input A, we move to the new state Q2, Q3, which is an accepting state since Q3 is an accepting state. And Q0, Q1 on B, we move to Q2, which is a rejecting state since Q2 was a rejecting state. Why did I did epsilon closure on Q2, Q3? Because according to the algorithm and according to the definitions that we used the letter A, but after we moved one step with the letter A, we can have additional transitions with epsilon. So after I compute where do I move on input letter A, actually using A one time, I have to continue and to do epsilon closure on this resulting state. Because, for example, I can have an epsilon transition, for example, now from Q2 or Q3 to Q0. So on A, I moved to Q3, but with additional epsilon transition, I can return to Q0. And with two epsilon transitions, I can go even to Q1. So according to the algorithms that we used, since we have to think about all possible transformations, so I have to use the input letter. I did it, A. But after using the input letter, I can look at all epsilon passes that I can have from the states that I reached. And it is called epsilon closure. So what I'm doing epsilon closure for Q2, Q3. Okay, we continue. So let's continue with the state Q2. For the state Q2, you have to define where once again, where do you move with A and with B? And after moving with A and with B, you have to do epsilon closure on the states that you have. The same idea that we did here.
Can you go back so we can see what's the original?
Yes, wait, clear all drawings.
Oh, it's up. Never mind.
It's
top left.
it's in the corner. Yes, it's at the corner of the slides.
So what's
Okay.
the rule? When do I do the epsilon closure that you did?
All
with
the
Q3
time.
and Q2?
All the time. Let's do it once again. Q2 on A, I see that I can move to Q1. And now I do epsilon closure of Q1.
But why?
Is because after moving with the letter A, you can have additional transitions with epsilon. And in equivalent DFA, that means that on input A, you can reach additional states.
And you need to reach only one state because it's DFA.
No, I don't need to reach one state. Yes, I need to reach one state, but one state that I will have in DFA can be the union of several states of NFA.
Okay, and the algorithm you were talking about, can we see the steps? Is it written somewhere?
Last lecture, you didn't see it?
Lecture 3?
Lecture 3, the second part of lecture 3.
Okay, I have it here.
That's what I did the whole lecture. I talked about equivalence of DFA and NFA. Okay, so let's do the next step for Q2. Okay, I'm looking to at the original automaton. Q2 with A, I can move to Q1. epsilon closure of Q1 is Q1 itself, since I don't have any epsilon transitions, so it was easy. Q2B, I have a self loop, so I stay at Q2. Epsilon closure of Q2, once again, we don't have epsilon transition, is Q2. So I add a self loop from Q2 to Q2 with B, and with A, I move to the new state Q1. So currently, let's see what we have. We already gave the solution for this state and for this state, and we have two more states to go. And you can continue in any way you like. You can choose Q1 to continue, and you can choose Q2, Q3 to continue. I will start with Q1 since it's simpler, it's only one state. And once again, the same idea. For Q1 and A, you have to define where you can go. You use A only once, but later you can use epsilon transitions. And for Q1 and B, you have to define where you can go. And once again, you use epsilon closure for your computation. So let's do it together. Q1A, where can I go?
Q2.
Q2 and additionally
Q3.
and to Q3. So I have with A several possibilities. I can go to Q2 and Q3. If I compute epsilon closure of Q2, Q3, I actually have the same state. I have epsilon transition from Q3, but once again to Q2. So basically, Q1 on A, we move to the state Q2, Q3 that we already have. And Q1 on B.
Just Q2.
Just Q2, and epsilon closure of Q2 is Q2. Okay, so let's go to our next part of the automaton. So Q1 with A, we now move to Q2, Q3. Q1 with B, we go to Q2. So now we have three states that we already finished dealing with. This one, that one, and Q1. So now I don't have any choices. I have to continue with Q2 and Q3. Once again, Q2, Q3 on input A, you have to define where we can move, and on input B, where we can move. So take your time, and we will do the solution together in a few moments.
Can I ask a question regarding this?
Yes.
If you have a state, like a double state, like Q2, Q3, what's the process that you're doing? You're applying A and B to Q2 and Q3 individually and then doing
exactly. And then unite.
You already did it in another state. Why can't you take it from another state? Why do you have to calculate it again?
You don't have to calculate. For example, for Q2, I have the results here. But for Q3, not yet.
Okay.
I will definitely use the ideas from Q2 here. Okay, so let's start solving this question together. Okay, so I'm taking the state Q2, Q3, and actually Wait, I will clear all annotations. Okay. So basically, for Q2 and A, I know that I go to Q1. Let's see where I can go for Q3 and A. Q3 and A, I can go, let's see. I can use 1A and go to Q2. So I definitely have Q2, Q3 on A, Q1, Q2. Then I will do an epsilon score of Q1 and Q2. And epsilon score of Q1 and Q2 is actually Q1, Q2, since I don't have any additional transition. So Q2, Q3 with A, I'm moving to new state, Q1 union Q2. Okay. Q2 with B, I stay at Q2. Q3 and B, the transition is not defined. So Q3 on B is actually an empty state. Q2 on B is Q2. So the union of empty state with Q2 is Q2. Epsilon closure of Q2 is Q2. So from Q2, Q3 on B, we go to Q2. Any questions?
What about C?
We didn't have C as an input letter here.
What is this with Q? It's epsilon. Okay.
Okay, sorry. Okay, we have a new state, Q1, Q2, and we have to compute where do we go for Q1 and Q2 on input A and on input B. But here I would like to teach you not a trick, but the whole idea. Please divide this Q1 and Q2, and you already have all the answers for Q1 and all the answers for Q2. Just combine, unite the answers. Once again, you can recompute from the beginning, but you don't need it. You already have the solution for Q1. You already have the solution for Q2. Just combine the solutions. So I will give you additional minute, and then we can do it together. I just would like to know if you finished. Okay, I will give additional moment. Okay, let's see. Q1 on A, we go to Q2, Q3. Q2 on A, we go to Q1. We unite Q1 with Q2, Q3, and we have a new state Q1, Q2, Q3. And Q1, Q2 on B. Q1 on B, we go to Q2. Q2 on B, we stay in Q2. So we unite Q2 with Q2, and we have Q2 as a resulting state. Oops. So with an input A, we have a new state Q1, Q2, Q3. With B, we return to the state Q2. Any questions? Okay, so we have additional new state Q1, Q2,
Sorry,
Q3.
Rina, yes, I have a question.
Okay.
So why is it an accepting state, the new state?
Because
Q1,
because Q3 is an accepting state.
Okay.
If you
So
have
everywhere
if you have in your new state, if even one state is an accepting state, the whole new state is an accepting state.
Also,
So
same
since
for the beginning. Q0,
the same from the
Q1.
beginning, exactly.
Okay, sababa.
Okay, so here you can divide, for example, this state as Q1 and Q2, Q3. You have Q1, you have Q2, Q3. You can also divide it in different way, whatever you want, but you already have the solutions at your current automaton, so you don't have to recompute everything. So can you tell me where do we move from Q1, Q2, Q3 with A?
Rina, you cut. It's only me, guys? Guys, can you hear Rina okay?
No.
No.
Me. And that's what the, okay, so help me. Q1, Q2, Q3, if we would like to define where do we go on input A.
Rina, you hear us? You hear us?
Yeah,
No?
yes, I can
Oh.
hear you. Yes, definitely.
Okay, no, you were stuck for 2 minutes. Okay.
Ooh. Okay,
So, okay.
Sorry. So the question once again, Q1, Q2, Q3 on input A, where do I go?
The same to itself.
The same loop, since Q1 on A is Q2, Q3, Q3 on A is Q1, Q2. We combine, we have Q1, Q2, Q3. Q1, Q2, Q3 on B.
Q2.
The Q2. And we finished building an equivalent DFAs, since we have new states. For each new state, we defined where we go on input A, where we go on input B. It's only one transition. So what we managed to build is an equivalent DFA. And actually, the algorithm is very simple. It just is that you have to do it slowly and not to miss some states. Okay, I have additional question or important comment for homework 4 and also for the rest of the course. And then actually we finished the practicing and I can answer all lecture related questions. I would like to remind you that if I have a theorem that if L1 and L2 are regular language, then the new language L, that is L1 some triangle L2 is regular, and we don't have the definition of what is triangle operation. So if I know that L1, L2 is regular, and L1 some operation L2 is regular, it doesn't say that if L1 a triangle operation L2 is regular, then L1, L2 are regular. Please pay attention, it's only one directional theorem. So here, I only know that if L1 and L2 are regular, then L1 some operation L2 is regular. If L1 some operation is regular, it doesn't mean that L1 and L2 are regulars. Let's see some examples. Okay.
What was regular again?
Regular, you have DFA or NFA. You have an automaton, finite automaton. It doesn't matter which automaton.
Okay.
The language is regular currently. Our current definitions, language is regular if you can build some finite state automaton that accepts it. Okay. I would like to give you several examples. 0 in power of n, 1 in power of n, intersection with 1 in power of n, 0 in power of n. Please take a moment and please tell me what will be the resulting language of this intersection.
The empty set?
No, think again.
Only once?
No.
Only, yeah, epsilon. Yeah.
Okay, you have an empty word. Empty word belongs to the first language and to the second language. Intersection will give us a language, a new language with only empty word in it. And we proved in during our lecture that the languages with empty word is regular language. We can build DFA easily, but so we have the result of intersection operation, and the result is regular. But original language L1 is not regular language, and original language L2 is not regular language. Why 0 in power of n, 1 in power of n is not a regular language? Please, let's look at this definition. I would like to accept, I will talk about L1 because L2 will be the same. So let's erase this one. I will talk only about the first language. I would like to accept all words that have a prefix of zeros and a suffix of ones. And the number of zeros in prefix equals to the number of ones in suffix. If I build a DFA, I have finite number of states. So I can count, but I can count until the last state. So let's say I have n states in my DFA. So I can count till n. And if I will receive the input word that have n plus 1 zeros or n plus 10 zeros, I already can't count. So I can't compare the number of zeros that I saw to the number of ones that I will see. So this language is not a regular language. Since I have to compare the exact number, I don't want to check if it's even or odd. Even and odd, we know that we can count. I didn't have a specific 5 zeros or 3 zeros that I also can count. But if I have n zeros and n is infinite number, I can't count till infinity with DFA. So what we see here, and what I wanted to mention, that was actually the comment of this slide, that if the result of some operation is regular, it doesn't mean that original languages were regular languages. And I would like to give you an additional example. Let's look at additional language concatenation. Let's use concatenation. I have concatenation of two languages. The first language, 0m1n. M is greater than n. So I would like to accept all words that have prefix of zeros, suffix of ones, and the number of zeros in prefix larger, greater than the number of ones in suffix, m greater than n. And I concatenate it with 1 in power of n, where n is greater than 0, greater equals to 0. So let's see. What will be the resulting language? And why I'm claiming that the resulting language is an accepting language?
Because
Let's say
M
that
and N are different numbers, so we can count each of them individually, maybe?
Yes, and when I have, let's say that I get something like this. And I have to prove that this language is regular. So after concatenation of prefixes of 0, suffixes of 1 with additional ones, I can always divide the input word into two parts like this. And I can claim that all the 0 part I've got from the first language, and all the ones I've got, and it is a concatenation of the second language. So the resulting language will be always the regular language, since I just have to check that we have zeros in prefix and ones in suffix. I will always claim that zeros belong to this language, and it always m is larger than n, since I don't have ones, and all the ones will always go to the second language, and the second language in any case was a regular language. And now when I have to build the result for this concatenation operation, I know that the result is a regular language.
It's a different n, though, right, for both languages?
Yes, because here it's a different n, since n is not related. You can use the same notation, but it's not the same n.
There n is 0 in your example, and n is 3 in the second, right?
Yes. If I don't have any zeros, no, but in this language, I have to have at least 1 0.
No, not zeros, ones. You would use the three
If
zeros.
I have only one as input, I should reject this word, because I have to have at least 1 0 in concatenation, because m is larger than n. M has to start at least from 1.
Yeah, I talked about the ones normally.
Okay. So another example, the concatenation here is a regular language. I defined, or at least I tried to explain why it's regular language. This language is not regular. This language is regular. So if the result is regular language, it doesn't mean that original languages were regular. And be careful, because sometimes when you prove your claims, you claim this part, and it is not correct. If the result is regular language, it doesn't mean that original languages were regular languages. Okay, we finished our practice for today.